So today in our tour, we're going to explore the Mineralogy and Petrology. So this is the oldest collection on campus. In total, the University of Alberta has 29 museums collections. I take care of 5, with all of the rock, minerals, fossils, meteorites, and specifically the fossils I take care of are the invertebrate fossils. Right? So if you want to learn more about those, there's another tour here just before noon that you take part in. And yeah, today we're going to explore unique things in the collection. So things you can't get. I'm going to take questions partway through, and then I'll take questions at the end. Okay, so let's begin. So the first specimen we're going to talk about is right here in the entrance to the museum. This is called a castanite. It is thought to be the oldest rock that we have on the planet. So this one here has been dated to be 4.02 billion years old. And there's not much rock left from the time when Earth's crust was forming, right? So we have plate tectonics on the planet, and we're constantly recycling our crust. And it's hard to access specimens that are this old. And right, it's covered with younger crust. And our continent our crust has been recycling with time. So this one here is 4.02 billion years old, and it came from the Northwest Territories. We have excellent radiometric dating labs on campus that help us age the rock, and we do that by using radiometric isotopes. So for example, this mineral here is a zircon crystal. When it forms, it can take in uranium into its structure, and then over time, that uranium is going to degrade to lead. And we measure the ratio of those two because as the uranium decays, it decays at a steady rate. And the ratio between those two isotopes give us the age. And so the University of Alberta is highly respected for its ability to do radiometric dating. We're going to go move into the museum now to the far corner and make sure we all know the difference between minerals and rocks. Follow me. All right, so we're over in the corner of the museum where we have a display called From Minerals to Rock. And this exhibit was actually designed to support not only university education, but grade school education as well. So in grade 3 in Alberta, we do have a unit on minerals and rocks. So some of you who are in attendance today might be familiar with the material I'm going to present. So let's see. Up front here, in this front row, we have an examples of minerals. They're all common minerals that we find in rock. Okay, so what's a mineral? A mineral has a steady chemical composition. So for example, this mineral here, this is halite. It's composed of NaCl, so sodium chloride. All pieces of halite, which is also known as rock salt, have sodium chloride. The one next to it is quartz. It's the most common mineral in Earth's crust. When you see sand, it's usually quartz. We'll talk more about that one later. It's all silicon dioxide. You can have just single element minerals. That's sulfur. It just has sulfur in it, okay? And minerals, besides having a unique chemical composition, they have a unique structure. So when we look at our halite again, it's made out of cubes. You can't see that right now, but if we were to see better pieces of halite, they do come in cubes. Biotite is a platy mineral. So this one here has about 3 or 4 sheets to it, but you can get them really, really thin, and the crystal grows in plates. So that's biotite. Okay. The quartz has prismatic crystal. So you can see that it's got a long crystal shape and it has nice pointy terminations. And quartz can take on a variety of forms, as we'll see. So in quartz, while some of its forms are informative, we have to be mindful that some minerals can take on more than one form. Some minerals have unique characteristics. So the sulfur, it smells like rotten egg. It's very stinky. And yeah, if you find a rock that has sulfur in it and you hit it with a rock hammer and quickly smell, you can smell the sulfur coming out of that. Pretty neat. So that's the mineral. Minerals are the building blocks of rock. And back here, we have examples of the three kinds of rock. So we're going to start over here, and we'll talk about igneous rock. Igneous rocks form from melt. So when you have molten rock, which is what melt is molten rock, and it's underground and we start to have solidification, you get big crystals, and the crystals grow together like puzzle pieces. This is an example of a very common igneous rock called granite. You might even have this rock in your home. We make countertops with it. Okay? So each of the different colors is a different mineral. Here is an example of an igneous rock that forms above the earth. So think about a volcanic event. When volcanic events happen, molten rock gets lifted above the earth, often in explosive ways, or in gooey ways, like at the volcanoes of Hawaii. And so this is pumice. Pumice is a frothy volcanic glass. And the rock hardens so quickly that there isn't time for big crystals to grow. So the rock traps gas bubbles, and it gives it a unique property. Okay, the gas bubbles in here are not connected, which makes this a really less dense rock than water, which means it'll float. So there's an example of pumice floating. Okay, there are other volcanic rocks that don't float. Their bubbles are all connected, or the density of the material making up the rock means that it doesn't float. Most igneous rocks do not, only pumice. Okay, let's talk about sedimentary rocks. Sedimentary rocks are those that form from broken down bits of other rocks. So if you've learned about weathering and erosion, we break down rocks with ice, water, wind, all of these different processes. They become little bits and pieces that can be put back together to make other rocks. Let's talk about sandstone as one example. So the sandstone is made up of little bits of quartz, which you already saw. It's made up of the mineral feldspar, which was also in that granite that you saw. And then we call them lithics. So lithics are bits of other mineral or rock. And so that's what's in a sandstone. And the sandstone grains are usually stuck together with cement. And it can either be silica, which is the building block of quartz, or it could be something like a calcite, which actually bubbles when you put acid on it. Pretty neat. Fossils are found in sedimentary rocks. And so this is a fossiliferous limestone. This one here is a big shell of a brachiopod. Back here we have a coral. And some of the bits of things that look like poker chips in there are called crinoid ossicles. And we still have crinoid ossicles around today because there's an animal called crinoids. Look them up, they're pretty cool. And yeah, fossiliferous limestone, all of fossils. Okay, the rock salt that you saw already, the halite, that's also an example of a sedimentary rock. The last ones we're going to talk about are metamorphic rocks. Here on this side we have gneiss. So the G is silent. It's a nice rock. Okay, and we know it's nice because it has banded texture. So metamorphic rocks form due to heat and pressure, and so the banding forms because of the layers separate out by different minerals based upon their density. And we also have that nice platy biotite all lined up in flat plates. Okay, so you can usually tell if a rock has been formed due to heat and pressure because you get the minerals lining up in the orientation of their crystal shape. You see banding and you see patterns that you don't see in igneous rock or in sedimentary rock. The last one we'll talk about is marble. Marble forms mostly due to heat. Okay, so that fossiliferous limestone we saw can be altered to marble. And marble is made of the same mineral as the fossiliferous limestone, the mineral calcite. We too use this for countertops and for wall coverings. We'll see building stone in a minute. But it's less hard than granite, for example, so it doesn't make the best countertops. So when we're deciding minerals to use in our daily life, we keep in mind the properties of it. All right, so I'm going to move this part out of the way and we're going to talk about meteorites. So meteorites are rocks from outer space. And so they can be either bits, they're most commonly bits of asteroids. They can also be bits of the moon moon. We have visits to the moon here at the University of Alberta. And they help us learn more about the history of the formation of planetary bodies, okay? And we can learn about how planets change over time by studying rocks. We can learn about early solar system history as well, because not all of the elements in these rocks are found in Earth rocks. Like early on, when the solar system was forming, the different elements formed at different times, okay? And so we can see different elemental compositions in meteorites. There are basically three kinds of meteorites, and we'll start here in the corner. There's iron nickel meteorites. These are really rare, and it's pretty much just iron nickel metal. The composition of this metal is unique. So when you're testing the ratio of iron to nickel in a meteorite, it's different than we find the kinds of rocks that have iron nickel on planet Earth. The one next to it is called a palisite. And so it's a mix of the iron nickel metal and then the mineral olivine. That's what the crystals are. The most common kind are chondrites. So the third one in the row is Bruderheim meteorite, and it contains more typical silicate minerals that contain carbonaceous chondrules, things like that. There's all kinds of unique terms for meteorites. We'll get it. Okay, before we move on and talk about something else, let's see a name you might recognize. Edmonton. The Edmonton meteorite was found in a farmer's field at the north edge of the city. And yeah, we name meteorites for where they fall or where we find them. Okay? So the Edmonton meteorite is found meteorite. The Bruderheim meteorite is a fall. It fell in March of 1960, okay, near the town of Bruderheim, which is just east of Budney. And people saw this meteorite fall, they saw the fireball, and then they went and collected specimens on their land. Scientists from the University of Alberta came out and collected them as well, and you can now find specimens of the Bruderheim meteorite from around the world. There's a link that will be shared with you in the chat where you can explore more about meteorites. Okay, and if you want to come see our meteorites, there will be a link shared that will tell you our hours. In general, it's Monday, Wednesday, Friday, 8:30 to 3:30. I'm going to be closed when I'm on vacation. You'll find a notification on the website to bring you the most up-to-date hours. Okay, let's motor on, and we'll talk about diamonds. What they help this mean to the Alberta Collection. Okay, at the University of Alberta, we have researchers that are studying how diamonds form and interesting things that they have on the inside, solutions. And we can even grow diamonds here at the University of Alberta using our research equipment. So it's a pretty special place. So we have a great big display of diamonds that I'll show you in a moment. But let's talk about how they form first. Okay. So here's a cross-section of the Earth. And as you go down, you've got the core. Then we work our way up to the mantle. And then above the mantle, we have our lithosphere. And up at the 150 kilometer mark depth in the lithosphere is where most diamonds form. Okay? So diamonds are carbon that structure is influenced by heat and pressure. So at that depth is a sweet spot for conditions for carbon to reorganize itself into diamond. But we know we don't mine 150 kilometers deep, right? So how do those diamonds get to the surface? At the bottom of the diagram here, we see that they come up from deep in the earth through a kimberlite explosion. In a kimberlite explosion, molten rock shoots out from below the Earth's surface, carrying those diamonds from deep below, and then everything falls back into this cone-shaped pit. Okay, in this cone-shaped pit, you're going to find rocks called kimberlite, which contain diamonds, and we'll see those in a second. And you can also find fossils, you can find bits of plant material in there. There's a lot of information that's recorded in the kimberlite rock about the layers through which the magma travels through. So they're pretty neat structures. Okay, so let's look at some diamonds. Okay, so we're starting off looking at native shapes of diamonds. So these are naturally occurring, they haven't been cut. And yeah, carbon is a unique atom and it can take on a wide variety of forms, right? So it's not surprising that we have different types of diamonds. Colors. Diamond can have different elements included in it, and it can be affected by impurities and defects, which give it the colors that you see here. You can get pink diamonds, yellow diamonds, clear diamonds. Okay. I wanted to show you some other forms of carbon just to show you how flexible it is. So we know diamond is the hardest mineral, right? And graphite is not. Graphite, we use it because of its soft properties. And so graphite is in your pencil lead. And because it's so soft, we can write on paper. Carbon is also what makes up coal. Coal is degraded plant material. And this is an example of coal from Alberta. This piece is pretty special because it also has this big chunk of amber in it. Okay. Before we take some questions, I'll just show you the rocks that bear the diamonds. So these are kimberlite rocks. And if you look at this one here with the red bits in it, those red bits are the mineral garnet. When diamonds are coming up to the surface of the earth, they also come up with garnets, the red mineral. You might have seen it before. We used it in birthstone and in jewelry and in sandpaper. So you might have encountered that one. Yes, so that's a bit about the minerals and rocks. We talked about meteorites, and we talked about diamonds. Let's pause and take a couple questions.
Yeah, so this is an interesting question. There's a myth going on around peanut butter being able to convert into diamonds. So they're wondering if you ever tried to convert peanut butter into diamonds.
No, that's one of those intermittent myths. It's not something we would try. Peanut butter doesn't even contain what we want to make diamonds with. And it's not something you can do at your home. You need to have really, really special equipment. And yeah, when we make diamonds here, you actually start with a really tiny micro diamond, and then you put chemical conditions around it so that there's a nucleus upon which the new diamond can form.
And another question is, why is sandstone called sandstone?
Yes, that one here is pretty self-explanatory. Sandstone is named for the size of the particle that makes it up. So when you get rocks breaking down into pieces, we classify the size of the sediment in different categories. So mud is the finest grain. Okay? Then you go your way up to sand. And sand has a particular particle size of sand. Further than that, we can have cobbles, we can have gravel. And so sandstone is named for the size of the particles that make up. All right, we have time for one more. Or if we don't, we'll just motor on. Lots to see. There's over 2,500 specimens you can see here at the university. And you can see Geology of Canada. We have rocks going from Western Canada to Eastern Canada. And right now, since we're in Alberta, we're going to explore some Alberta rocks. They're right behind the camera person here. Okay. So the geology of Alberta at the surface is quite young. The rocks that we have on top, a lot of them are related to the glacier deposits when the glaciers last went through. In Edmonton here, the glaciers last left around 12,000 years ago. And we get a lot of rocks related to lakes and something called hills, a mix of materials that are dumped by the glaciers when they were last through here. But at the oldest, we have rocks that are billions of years old. So these come from the continental backbone, or we call it the Precambrian basement. And there's metamorphic and igneous rocks deep below the crust we see at the Earth's surface. And you'll notice that the core shape of the specimens, and that's how we collected these. So you use a big drill, a circular drill, and you drill deep, deep, deep in the earth, and you pull up these big cores of rocks. Up in the Canadian Shield area of the province, you can access some of these materials up the surface, like really old rocks up at the surface from the Canadian Shield. But if you want an example across Alberta, we do have to do the drilling. Okay, most of the rocks we encounter from these are sedimentary rocks. For much of the past billion years, we have been covered by oceans. Okay. Pardon me. So we're going to see things like limestones. We're going to see fossiliferous limestones. There's an example of one there. Okay, at the far left, you're going to see a sandstone. It has iron, which is why you see those red streaks. We have evidence of ancient volcanoes. Up there's a volcano ash with fossils in it. So that's an example of an igneous rock that we find near the surface. Last kind of rocks I wanted to talk about are another kind of sandstone. Lots of sandstone in Alberta. We've had lots of ancient rivers and coastlines. Let's have a look at this quartz granite here. It's the white sandstone. It's mostly quartz. Okay, so in that other sandstone, it's a dirtier sandstone. It has quartz, feldspar, and lithics in it. Almost 100% quartz in that one. What's unique about that kind of sandstone up in the McMurray Formation is sometimes it contains oil. And so that's oil sand. So the rock next to it, with the layers you see, is a sandstone that has bitumen in it. And bitumen is it's a hydrocarbon, and it's peanut butter thick. Okay, and the oil sands are a resource that are used to produce oil and products that we use in our daily lives. And what's unique about the Alberta connection is that our scientists initially did the mapping of the areas where the oil sands were. We're learning more about how the oil got there, because it wasn't formed there, it traveled to those sands. And we help people map and plan where to drill for oil and gas. And so our scientists do a lot with the hydrocarbon industry, and that's been around for like 100 years. In terms of getting the oil from the sand, Dr. Carl Clark figured out a process that's still used today around the world for working with oil. That's a unique to Alberta story. Okay, let's go talk about quartz. So quartz silicon dioxide forms in a tetrahedron shape. If you're familiar with the tetrahedron shape, it's like a pyramid, 4 sides. Okay. And so it's a very flexible structure. And you use quartz in your daily life as sand. It's an abrasive. Can be made out of countertops. We use it in jewelry. We also use it just as a stone, right? That we collect. Here's a couple that people collect. There's amethyst, which is purple. And the purple color is from natural occurring radiation in the ground interacting with the quartz structure. And so it creates purple color because the structure changes. Rose quartz can actually be turned pink because of titanium, iron, or these manganese or magnesium, one of those two, and it gives it the pink color. Agate is another stone that people collect. Okay. And you may have heard that crystals can have healing properties. So some people use stones in their daily life for improvements in mood and for healing. And there's no scientific evidence for that, but it is a cultural mineral. Okay, so let's go look at some more cultural use of minerals. We're going to head to the corner. So on the top shelf here, we have gemstones. And what makes a gemstone a gemstone? A gemstone is a mineral that we give economic value to, and it's valued for its purity. Okay, so it's a special kind of mineral. The minerals that we use in our daily life otherwise can either be metals or they're industrial minerals, and they have special terms for what we use in our daily life. What's special about these is that they're birthstones. Okay, you might know what your birthstone is. Mine is aquamarine because I'm born in March. Sapphire is for September. And if you want to see what your birthstone is, you can take a quick look at this chart here or look it up later. Something that's interesting is that birthstones have been around in different cultures. And so there are different birthstone systems. So if somebody tells you, my birthstone is garnet, and then somebody else in the same month tells you, my birthstone is corundum, both could be right, because these are cultural constructs, and people around the world have different birthstones. Okay, so let's get to something that's more daily functional, building stones. So up at the top, we have building stones that you can find at the University of Alberta. And the one in the upper left corner here is Tyndall stone. You can find that stone all around Canada. And it comes from west of Manitoba. It's 380 million years old. It's a limestone with burrows in it. So all of those dark brown colors are burrows. Keep an eye out for that stone around Edmonton. It's very common. More commonly, we use things that are igneous because they're nice and hard. Or we use slate, which are metamorphic rocks, which are hard and resistant to weather. Okay. Building stone has been around for thousands of years. You think of the pyramids in Egypt, they're made of limestone. You can actually see fossils in there. I've never been, but there's huge disc-shaped single-celled creatures in there. I'd love to see them in real life in that rock, maybe one day. Okay, another rock that we use in our daily life. Examples of it from Alberta. So on the top shelf, we see gypsum. Up here, and then I have a piece closer. I'll show you in a second. This is from Peace River. So where do we use gypsum? Okay, if we look at the wallboard, where do I have wallboard? I don't have wallboard because everything's laminated. Okay, wallboard, your walls in your house. Okay, wallboard contains gypsum, and gypsum is selected to be the filling of wallboard because it's first insulative. More importantly, it's fire resistant, and it also helps dampen sound. Okay, because it's really heavy. Heavy materials dampen sound. Just the gypsum is a very important material in our life. It's really soft. Not something you want to breathe in. It's kind of gross. In nature, gypsum comes in many forms. You might have seen something called gypsum roses. In BC, Saskatchewan, and Alberta, in rocks, we can find gypsum crystals called selenite. So when you're hiking around the Badlands, take a look the next time. You might see these sticking out of the sediment. Okay, it's important to leave them there. We don't go picking stuff out of the nature in parks, right? And yes, so that's the gypsum you encounter every day. All of these flat walls in the museum are economic minerals. They're minerals that we use in our daily life. And some of them are easy to refine, right? So this is the mineral fluorite in a big green mass. You can break up that fluorite quite easily and get what we use out of it to process steel. That's the most common use for it. Okay, the rock next to it is more typical of what you see for an ore. So you get a mix of minerals. The fluorites in that one too, but you have to do a lot of crushing and chemical processing in order to get the fluoride out. And or fluorine, depending on what you're using. And this creates sustainability issues, right? And in Canada, we've had mines come and go over time, and they've had different environmental impacts. What makes our Alberta conditions collection special is that we do have a lot of specimens from past mines. Before we leave our minerals, we're going to pop over here and look at Beryl. Okay? And you'll notice that these specimens are coming from all over the world. This one comes from Colombia, the US, Manitoba, okay, and Quebec. This one here is from New Hampshire. Why do we have specimens from around the world, and how did we get them? People ask me all the time. Most of the minerals were collected early in the department's history, and we were fortunate to have a patron. A patron is somebody who helps you do something, either with physical help or financial assistance, and they do stuff for you that's very our patron was William Ferrier. William Ferrier collected and purchased minerals for museums all across North America. It was very important to him that we train up geologists. So in the 1910s, he was regularly purchasing and donating specimens, and he would travel the world to do this. He was so important to the University of Alberta that he was the first person to receive an honorary doctorate here. And without William Ferrier, we wouldn't have all of the wonderful minerals that you have. And something to be mindful about is we wouldn't be able to collect these minerals today because as time has gone on, we've improved our practices in terms of legislation to protect mineral resources. And we've also changed how we work with the environment, right? And so there are fewer mines than ever before. People aren't allowed to go picking stuff up wherever they happen to be. and we have to follow the rules for accessing earth materials. All right, so we're going to motor on, and I will show you one. Oh, there it is. People ask me what my favorite one is, so I may as well show it to you while we're here. It's this specimen here. That's called peacock ore. And so it contains some minerals, chalcopyrite, which is the bronzy one, and the bornite is the bluey purple one. Okay. What's neat about this one is it's really pretty. That's why I like it. It's also neat because whether you're looking at chalcopyrite or bornite, it contains copper, iron, and sulfur. The only thing that differs is the kind of the element that's in there. Okay, so there's a different form of different amount of sulfur and the form of sulfur in chalcopyrite versus bornite. Why is this in the economic case? Chalcopyrite is a copper-bearing ore. Okay, copper is used in wires, in your cell phone, and it can be lots of pans, right? We've been using copper for thousands of years on the planet. Okay, let's see some more stuff. We're going to just pop in here and see some metals in an exceptional presentation. Okay. Let's start with this one. These are copper wires that formed in nature. Okay, this is extremely rare. Here in the back corner, we have examples of gold in great big masses. This is also really rare. Okay, when we usually find metals, the copper is usually tied up in other minerals like that chalcopyrite saw. The gold, we can find it in the quartz, but it's in little veins usually, and you can't even really see the gold with your eye. So when we're producing metals, we take lots and lots of rocks and we break it down to get this very small amount of metal. And when you're seeing fancy pieces of metal on display places, know that that's very rare. And most of the stuff that we produce for our daily lives comes from lots and lots of metal. Okay, we're going to pop in and look at some fluorescent minerals. Fluorescence, here I'm going to come down a little so that we can see. Okay. So fluorescence is a mineral property. Not all pieces of mineral are fluorescent, and it's a unique physical property of some pieces of some mineral. We'll see how this works. So right now, we're looking at these stones with all of the energies of light involved in visible light. Okay, and so the light is hitting the rock and it's bouncing back to our eyes, and the energies of light tell us what color we're going to see. Okay. When we look at the property of fluorescence, we're only going to look with UV light. UV light is really high energy, and it's the light that gives us sunburns. Okay, so I'm going to suggest that you pick one. My recommendation is that you pick scapholite, maybe that sphalerite there, or this fossil, and we'll see what happens. So it's going to go dark, then I'll turn on the UV light. Okay, so right now we're only seeing with UV light, and there's something happening here, so we can see some glow. So this is much different than a reflected light process, right? But you can see the colors are different than the original mineral. And if you watch the sphalerite there, the orange one in the middle, it's going to stay glowing after the light goes on. All right, we'll turn on the light. So what is happening? What's happening is under UV light, sometimes in the initial surface layer of the mineral, there are electrons, which are charged particles that get really excited, and they go up to a higher energy state. And when they fall back down, they give off a photon of light. And so you're actually seeing that light that was generated from that electron fall back into position. The sphalerite, you saw that when the light went out, it still glowed for a while, didn't it? That's actually a property called phosphorescence, when it has that ability to keep it. It takes longer for the process to stop. Okay, so it's cool, it's fun. How do we use it in science? Okay, you saw the fossil. It was easier to see under the UV light, right? And to distinguish between the rock and the fossil. And so I would use it for photography. I think that picture would have looked a lot nicer than this one, right? When I'm looking for uranium-bearing minerals, so that's some of the blocks up here is uranium-bearing. Okay. Oftentimes professors are looking for uraninite for research purposes, and uraninite will occur with other black minerals that don't fluoresce. So if I bring my specimen in here and put it under the UV light, then I can see where the uranium-bearing section is. So it is a useful property. Those are really cool. All right. We're going to leave this area, and we'll take our final stop at the Whitecourt meteorite case. Okay, so up in Whitecourt, Alberta, meteorites were found, and but they're also associated with a crater. But the crater was really hard to see. So at the University of Alberta, we used a special technique to see through the trees. So look at these photos. On the left is what the landscape looks like there with the trees on it. So all that dark stuff, that's vegetation, trees. And then you can see where the river is flowing. It's where there's no trees there. On the right, there's no trees. And you see that big circle? That's the crater, okay? By using LiDAR techniques, which is a way of using laser light, and it reflects back and gets captured, and the data can be used to make that picture without the trees. We've learned a lot about the Whitecourt meteorite because of being able to map it properly, right? The directionality of the meteorite can be, you can get to studying that crater to that degree of examination. How big is the crater? Let's look in the middle. You can see that there's a little person there for scale. Okay. And then there's a person at the top too, if you can see them through the trees. So it's actually a really big crater. Okay. It's so big that if you were walking the landscape, you might not even notice that you were walking through a crater, right? You might just be thinking you're walking through any depression. So the LiDAR was really helpful at determining that, yeah, this was totally a crater, and we didn't just have meteorites from a fall that didn't leave it very well. Okay. We've talked a lot about meteorites, okay? It's actually rare for universities to have lots of meteorites. The University of Alberta has over 1,400 pieces of meteorites, and they come from over 3 different places around the world. And we've had an active meteorite researcher on campus starting in the 1960s, and we have one still today. So this is Canada's largest collection of meteorites at the university, and we lend specimens around the world so people can learn more about meteorites. All right. So just to wrap up, inside your chat, the facilities information about when you can come to visit will be there. There should be a link to a virtual tour for you so that you can go and visit us at any time, okay? But yeah, if you want to come for a visit, we will be open Monday, Wednesday, Friday. So I hope you have a chance to come out and learn more about rocks and minerals and see some things that are unique to Alberta and the collections here at the University. We have some time for questions.
Alright, so how many rocks are in this museum?
That's a great question. I usually put that in my introduction. In this museum on display, there's about 2,500 pieces. As part of the Mineralogy and Petrology collection, I have over 15,000 of rocks and minerals. But that's only the formal collection, so the museum's part. At the university, you have rocks and minerals that are collected by researchers, and they're considered part of our research goals. So there's going to be thousands of rocks that are part of the research collection. We also use rocks and minerals for teaching, and the students can test those, and so that over time they get scratched and worn out. And there are going to be hundreds of specimens in our teaching collection. So it's actually quite impressive to put them all together.
And which diamond is the rarest diamond?
I don't know the answer to that question. I'm imagining it's going to be the biggest one, right? That's a great question for Google. I'm sure lots of people have asked that one.
Is coal like diamond at all?
Yes, coal is like diamond and all. Diamond because it is made out of carbon. So, and all that's different is where they form and what the heating pressure was like. Coal also forms from degrading vegetation. It's a bit different that way, but yeah, the similarity is.
Do you know why birthstones are called birthstones? Or why we use them as birthstones?
I honestly don't know the history on that and where it started. Something I forgot to mention about coal. Coal is only like 100% carbon when it's anthracite coal. Usually it contains degrading bits of plants, so it's hydrogen, oxygen, nitrogen, and it can contain other impurities.
So one of our attendees heard that peacock ore is manganese, and they were wondering if that's true or is it not?
Yeah, when you're looking around at different places for purchasing minerals and rocks, you can recreate some of the things that we see in nature in the lab. So you'll find amethyst that isn't real amethyst from nature. You'll find agate that's been colored artificially afterwards, particularly specimens that come from Brazil for agate have been colored. And so yeah, you have to be careful when you're looking around. Bismuth, if you see these gorgeous bismuth crystals, which is a metal that can have kind of a rainbow color sheen to it, most of those are artificially made. When we find them in nature, they look more just like a metallic stone. They're not as impressive.
What's the rarest rock in the world?
I think we saw it. It's the oldest rock. Okay. If you think about how big the planet is and how hard it is to get to really, really old rocks, we have lots of crust on top of our really, really old rocks that form the continental backbone. It's going to be the oldest rock.
And someone is wondering if we could show them the biggest diamond that we have here.
Okay, I have diamond models, and so we'll go look at those. They're in the far corner where the birthstones are, so we'll take us a second to walk there. Okay, so just like we have replicas of fossils to share with people around the world, people make glass models of diamonds so that we can share them with people around the world. So the biggest one is the Great Mogul at the back there, and it's currently missing. Okay, that happens, right? Over time, if you have one thing that's really precious, they get lost. It's like paintings and anything that we value with time, things get lost. Things get lost in my collections. You know, over time, our collections are over 100 years old, and things get misplaced, labels get separated, we get mice in the collections, and the mice eat the labels. It's actually really hard to keep something precious for a really long time.
All right, so we're ending the end of our time here. So thank you so much for showing us this tour. Do you have any closing remarks?
Closing remarks. There are a few places on campus you can come visit to see more and learn more about earth science. So besides this museum, down the hall in the basement of the Earth Sciences building is the Paleontology Museum, where you can see fossils and explore life through time. Outside, just north of the Earth Sciences building along Saskatchewan Drive, we have a walkable Geology Canada in Boulder form, and it's called the Geoscience Garden. There's a great companion website so that you can even explore that one from home if you can't make it in to see it in person. Inside the buildings of Earth Sciences, as well as in the Biological Sciences building, you're going to find fossils displays and other natural history displays in that building and mine in the hallways. If you visit the anthropology area in the Tory building, you'll see displays there as well. So I'd encourage you to check out the University of Alberta Museums site, which lists all of the collections. I'll tell you which one is my favorite. The clothing and textiles students. In human ecology building, there are students who are working on courses with the curator of the clothing and textiles collection, and they'll do student-driven exhibits, and they change regularly because the students are doing for their courses, and that tends to be something that's really relevant because we use clothing right every single day and through time, and it has social justice implications. So yeah, please explore. There's a lot of museums to explore on campus.
All right. Well, thank you everyone for joining us today, and we'll see you at our next event.